One of the most important concepts of the Laplace transform is the convolution theorem. So the convolution theorem allows you to take the Laplace inverse of one function multiplied by another, which can sometimes it cannot be broken down by using partial fractions, right? So I'm going to start with this example. So if you are asked to take the Laplace inverse of this function, let's say a divided by s squared plus a squared, the Laplace inverse of this one is sine of at, right? But that is multiplied by s divided by s squared plus a squared, and this is cosine of at. So this is sine of at, this is cosine of at. So, but how do you take the Laplace inverse of the product of the two? So, in taking the Laplace inverse of the product of the two, we can take the Laplace inverse of them separately. So, the Laplace inverse of the first one, which is a over s squared plus a squared. Right, but this is not normal multiplication. This is going to be what is going to separate them is this asterisk sign, and then we are going to have the Laplace inverse of the second one. The second one is s over s squared plus a squared. Right, so this one is not multiplication. This is what we call the convolution. So let me write it here in a different color. The asterisk sign is what we call the convolution. Right, so the Laplace inverse of the product. So if you have the Laplace inverse of the product, that is a over s squared plus a squared multiplied by s all over s squared plus a squared. This one is normal multiplication. This is equal to the Laplace inverse of this one is sine of at. So this is sine of at, right? And this is convoluted. This is not multiplication. This is convoluted with the Laplace inverse of this one is the cosine of at. Right, so this is what we have. So remember, this one is not the normal multiplication, not multiplication. So how to pronounce that is sine of at convoluted with the cosine of at. So how do you define a function f of t convoluted with another function g of t? So let me write the definition of the convolution here. So let's say this sine of at is f of t, right? Convoluted with another function. Let's call that function g of t. Why not? So this g of t is also cosine of at. What is the definition of this one? This is equal to the integral from 0 to t of f of t minus another variable, let's say tau, and then multiplied by g of tau and then d tau. This is the definition of the convolution, the convolution of f of t and g of t. So this is pronounced as f of t convoluted with g of t. Right, so now the task here is to, how do you take the Laplace transform of the convolution? So let me do it in a different color. So now the task is, how do you take the Laplace transform of the convolution, that is f of t convoluted with g of t? I must warn you again, this one is not multiplication, that is just simply convolution. So the Laplace transform of f of t convoluted with g of t, we already know what the Laplace transform is. That is the integral from 0 to infinity of e to the negative s times t, right? And we are going to multiply by what we are going to transform. And what we are going to transform is f of t convoluted with g of t, which can be replaced with the definition. So I'm simply going to write the definition here. The integral from 0 to t of f of t minus tau. This is multiplied by g of tau and then d tau. This is what we are transforming. But don't forget that if you are writing the definition of the Laplace transform, you have to bring the dt. So this dt is with respect to the first integral. So this is what we have after the definition of the Laplace transform of the convolution. So the Laplace transform of f of t, which is convoluted with g of t, this is equal to the integral from 0 to infinity. This is the first one, and the second one is the integral from 0 to t Now we have e to the negative st. This is multiplied by f of t minus tau. This is multiplied by j of tau, and then we are going to have d tau and then dt. So we have a double integral. Which one are we integrating first? So the first one here corresponds to the integral here. So that means we are integrating first with respect to tau and then later on with respect to t. But I would want to switch these limits of integration. I want to switch so that I'll be able to integrate first with respect to t and then later on with respect to tau. But the region upon which we are integrating is not rectangular, so we can't easily switch the limits of integration using the Fubini's theorem. What we can do is to draw this region and then redefine the limits of integration, and then we can switch the limits. So I'm going to go ahead and draw the region upon which you are integrating. So first of all, let's find what t is. So that means t is starting from 0 to infinity. So t is equal to 0 for the lower limit and infinity for the upper limit. Tau, what about tau? Tau is equal to 0 for the lower limit. I'm sorry, this is tau. So tau is equal to 0 for the lower limit and tau is equal to t for the upper limit. These are the limits of our integration for tau. So now we are going to draw the region. So let me call this one the tau axis and call this one the t axis, right? So first one, tau is, t is equal to 0. When t is equal to 0, it means we are just moving along the tau axis like this. This is t is equal to 0, moving along the tau axis. So this is t equal to 0. To t is equal to infinity. Infinity is a very big number, but let's say infinity is somewhere here. Why not? So that's infinity, so it moves like that. Cool. So it moves this way. This one's a little bit better. So now what about tau? Tau is equal to 0 for the lower limit. So when tau is equal to 0, it means we are moving along the vertical axis. That's the t axis. This is tau equal to 0. So this one is t is equal to infinity and this one is tau equal to 0. And the last one is when tau is equal to t. So tau is equal to t, and then we have tau and t axis. That means tau is equal to t is just a line passing through the origin like this. So this is the region in which we are integrating, right? So this region, this is the region that we are integrating. This is the region. You see, it is not rectangular, it is triangular. So it means we have to redefine the limits here. So I want to integrate first with respect to t, and t is the vertical axis. How am I going to modify this limit? So to modify this limit, I will have to move vertically. So t is moving from here, right, all the way to infinity like this. This is the area upon which I are integrating with respect to t. So t is going to start from this. I forgot to write this. Right, so this one is when t is equal to tau, right? So t is moving all the way from tau here to infinity. So those are the redefined limits for t. So if I'm writing this one, that is going to be what? So I'm going to have the Laplace transform of f of t convoluted with g of t, and this is equal to now I'm going to have the integral, and then I'll have this e to the negative st. This is multiplied by f of t minus tau and then g of tau, and I'm going to integrate first with respect to t and then later on with respect to tau. So this one is going to be the limits of integration for t, and then t is moving from what? Tau. So the starting point for t here is from tau all the way to infinity here. So the limits of integration for t is from tau to infinity, right? Now what about the limits of integration for tau? Tau is starting from this point, right? Tau is starting from 0 and is moving all the way until it meets t, right? Like this. So tau is going to start from 0 to t, right? But t itself is moving from 0 to infinity. That is the highest value of t here is infinity. So tau is going to move from 0 to infinity. So these are the redefined limits of integration. So that is now integrating first with respect to t and then with respect to tau. And now these ones are the limits of integration for t. Alright, so now we can integrate this. We are now going to do a substitution. So let me rewrite this. The Laplace transform of f of t convoluted with g of t. This is equal to the integral from 0 to infinity. This g of tau has nothing to do with t, so I'm going to bring it here. G of tau, then the integral from tau to infinity of e to the negative st. This is multiplied by f of t minus tau, and then dt, and then this one is closed, and then d tau outside, like this. So cool, now we are going to do a substitution. So I am going to let's say u, I love u, substitution, u to be equal to t minus tau. That is this one here. I'm going to let u to be equal to t minus tau, right? And we are going to integrate this one, differentiate this one with respect to t, because we are integrating with respect to t. So here it means du dt is equal to 1. This is a constant when you are differentiating, so implying that du is equal to dt. Alright, so that means in place of dt, I'm going to replace that with du. Now, what about the change in limit? When t is equal to tau, that is the lower limit, and what is going to be u? U is going to be, replace t with tau, is going to be tau minus tau, and that is going to 0. So what about when t is equal to infinity? This one you have u to be equal to infinity minus tau. Tau is just a constant here, and that is going to be infinity as well. So the limits of integration will change from 0 to infinity. Now what about t? How do you find an expression for t here? So it means t here is equal to u plus tau, like this. So that is just by isolating tau from here. T, not tau. So now let's take the integral into the u world. So we have the Laplace transform of the convolution f of t convoluted with g of t, like this. This is equal to the integral from 0 to infinity of g of tau. And now the inside integral is going to be the integral, the limits of integration is now from 0 to infinity, right? And then we have e to the negative s times t. T can be replaced with u plus tau. That is u plus tau, like this. And then f of t minus tau can be replaced with u. So this is f of u. And dt is the same as d tau. That is what we have here. Dt is the same as du. I'm sorry about that. So replace dt with du. And then this d tau is already outside. That is this one. Now let's apply the laws of indices here. So the Laplace transform of the f of t convoluted with g of t, this is equal to the integral from 0 to infinity of g of tau, and then the integral from 0 to infinity of e to the negative. Now this is going to be su multiplied by e to the negative s tau, right? And then we have f of u, and then du, and then d tau. All right, so this one is a constant in the u world. This one, it has nothing to do with u, so I can bring it here. So this one is going to be the integral from 0 to infinity of g of tau. I'm going to bring this one outside the integral, so that is going to be e to the negative s tau. And then we are having the integral from 0 to infinity of e to the negative su, and this is multiplied by f of u, and then du, and then d tau. Now you can see it clearly, right? So the Laplace transform of the f of t convoluted with g of t, convoluted with g of t, is equal to this. So this one is equal to, now I want to write this one first. So that is going to be the integral from 0 to infinity of e to the negative su multiplied by f of u, right? And then du, and then this integral, that is going to be the integral from 0 to infinity of e to the negative s tau. This is multiplied by g of tau, and then d tau, like this. And this is the Laplace transform of f of t convoluted with g of t, like this. Okay, cool. So now looking at the definition of the Laplace transform, what is this one? The first one is the Laplace transform of the function f of u, and the second one is the Laplace transform of the function g of tau. So this is equal to, the Laplace variable here is equal to s, right? So this one is going to be the Laplace transform of the function f of u. This is multiplied by, this is normal multiplication, not convolution. This is multiplied by the Laplace transform of the function g of tau, like this. And this is the Laplace transform of f of t convoluted with g of t. So now the Laplace transform of f of u, right? This one is capital F of s. The Laplace variable here is s, times this one, the Laplace transform of g of tau is capital G of s. And this is the Laplace transform of f of t convoluted with g of t, like this. Cool. So we have established the result. So the beautiful result is that, let me write in a different color, in white. So the beautiful result is that the Laplace transform of the convolution, that is f of t convoluted with g of t, this is equal to f of s. This is multiplied by g of s, like this. So this is the convolution. So that is why if we take the Laplace inverse of this guy, we are going to return the convolution. That is what I started with. So when I started with an example. The Laplace inverse of these ones multiplied to each other is the Laplace inverse of this one times the Laplace inverse of this, right? And that is going to return the functions. So that means that here, right, let me show you. That means that here, if we take the Laplace inverse of this, that is f of s multiplied by g of s, right? This one is going to return the convolution. The convolution here is f of t convoluted with g of t, like this. So this is the property of the convolution. So now let me use it to do something fun before we wrap up the video. So with this one, let's look at these two examples. So let's say you want to find the Laplace transform of something like this. So let's say sine of t, right, convoluted with g cosine of t, convoluted with cosine of t, like this. And now the second one, let's say another example here, we are going to find the Laplace transform of sine of t. This is multiplied by cosine of t. The two are different. You have to be careful. The two are different here. So the Laplace transform of sine of t convoluted with with cosine of t. But this one is the Laplace transform of sine of t multiplied by, so this one is multiplication. Multiplication, the normal multiplication we know. And this one is convolution. Convolution. So the two are completely different, and the Laplace transforms of these two will be different. So now let me do them separately. So the first one, the Laplace transform of the sine of t convoluted with cosine of t. This one is equal to, just using the formula that we derived. So the Laplace transform of the convolution f of t convoluted with g of t is equal to capital F of s multiplied by g of s. So this one, that is just going to be the Laplace transform of the sine of at, right? And this is going to be multiplied by the Laplace transform of the cosine of at, like this. That t, not at, I'm sorry about this. So this is the Laplace transform of the sine of t multiplied by the Laplace transform of the cosine of t, like this. So this is just by using our definition, right? So the Laplace transform of sine of t is 1 all over s squared plus 1 squared, which is 1, multiplied by this one, cosine of at, the Laplace transform is s all over s squared plus 1 squared, which is 1. And this is going to yield s all over s squared plus 1 all squared. And this is the Laplace transform of the convolution sine of t and then cosine of t. Right, so that's the first one. That is very easy. So, but this normal multiplication, we want to find the Laplace transform of this normal multiplication. This is just sine of t multiplied by cosine of t. This is different from what we from the convolution theorem. So this one is equal to the Laplace transform of, this one is 1/2 times sine of 2t, right? Because sine of 2t from the double angle identity, you know that sine of 2t from the double angle identity is 2 times sine of t and then cosine of t, right? So that means if we divide here by 2, we can do the same thing to the right hand side, and then this will cancel that. Then we'll have sine of t times cosine of t to be equal to 1/2 times sine of 2t. So this is what we have. This is a very simple one, and 1/2 is a constant. It comes out of the Laplace operator. Then we have the Laplace transform of sine of 2t, and sine of 2t, the Laplace transform of that is 2. This is 1/2 in front, then we have 2 divided by s squared plus 2 squared, and 2 squared is 4, and this one is going to be 1 all over s squared plus 4, right? So we see that the Laplace transform of sine of t multiplied by cosine of t, this one is equal to 1 all over s squared plus 4. So you see that the two are different. So the Laplace transform of sine of t convoluted with with cosine of t, that is going to be s over s squared plus 1 all squared. But the Laplace transform of sine of t multiplied by cosine of t, that is going to be 1 over s squared plus 4. So this is the convolution theorem. So it is very important in solving the Laplace inverse of some complex functions. If we can't use partial fractions to break the function down, then we might have to resort to the convolution theorem. So the theorem simply states that if we have f of t convoluted with g of t, right, which is defined this way, the Laplace transform of f of t convoluted with g of t is just the Laplace transform of f of t multiplied by the Laplace transform of g of t. That is what we established from our proof. And then that is the convolution theorem. So this is part 1 of the convolution theorem. In my next video, I am going to use this convolution theorem to find the Laplace inverse of some of a particular function that will be impossible to break down using partial fractions. So if you like the video, give me a thumbs up and then subscribe to Calculus Diaries, and I'll see you in my next video where we use this property to solve the Laplace inverse of some functions. I thank you so much, and I'll see you in the next one. Bye bye.